Good morning, good afternoon, good evening, everyone, depending on where are you joining this meeting. Welcome to the fifth webinar series on digital twins. And we are focusing on AI machine learning for digital twins this week. This is the fifth of the webinar series. We're going to continue this on a monthly basis. And the focus of this week is on artificial intelligence and machine learning, which becomes the enabler for digital twins, especially with large data sets or big data sets produced by different sensors. And today we'll be chaired by Dr. Liang Zhao. He's a leader on AI machine learning, including different types of frontiers of AI machine learning. Dr. Zhao is a professor at Emory University, and he has been chairing several sessions in the domain. He's definitely one of the leaders. So Dr. Zhao, please go ahead.
Okay. Thank you very much for your introduction to me. So today we're gonna pretty much talk about the topic on AI for digital twins. And we are happy to invite several very outstanding researchers in this area. Dr. Song Gao, Dr. David Page, Dr. Gengchen Mai, and Dr. Douglas Rao. So we're going to start with the two keynote talks. One is from Dr. Song Gao, and the other is from Dr. David Page. So for each keynote talk, it's going to take roughly 30 minutes, and then we encourage the audience to ask questions at the end of the talk. So let me first briefly introduce our first speaker, Dr. Gao. So he is an associate professor in the University of Wisconsin-Madison and the director of the Geospatial Data Science Lab. He graduated as a PhD student and from the GIS Science of the UCSB. He is a very famous researcher in the topic of AI for geo data science, and also their applications in many sub areas like the human mobility, social science, and spatial networks. I mean social sensing. And he got many awards, such as top 1 highly cited researchers, UCGS Career Award, and so on. Due to the time limit, I cannot enumerate all of them. And his today's talk name is Understanding Food Supply Network Resilience, right? Via spatial knowledge graph and AI. So let's welcome him to start his presentation.
Yeah, thank you so much, Dr. Zhao, for your kind introduction, and then also Dr. Yang for kind invitation. So let me share my screen and just to check. Okay, so is the screen sharing okay? Okay, good. Yeah. Thank you very much. It's my great pleasure to present in the webinar series. And today my talk will be about understanding food supply network resilience with geospatial graph and AI. So I will start with the key mission of our NSF-funded AI Institute, ISICO, which stands for the Intelligent Cyber Infrastructure with a computational learning in their environment. So in our AI institutes, the core mission is to create the AI-powered standardized cyber infrastructure that can support various kinds of computing. For example, the classic scientific computing in their PC, or the fast evolving cloud computing or HPC computing and on-field computing, and also co-design with use-inspired sciences such as animal ecology, smart food sheds, and digital agriculture. So today I will be focusing on one of the use cases about the smart food sheds. So we are utilizing various kinds of advanced AI technologies, including like knowledge graph, model commons, adaptive AI, federated learning, and conversational AI. So due to the time limit, I will only talk about some of them. So back into the domain science question. So the definition of a food shed, which is actually a concept highly relevant to geography and analogous to the watershed, which describe the catchment of the sources of the food for a region. So which is a concept also posted at the Annals AAG, which is the flagship journal in geography. So for this mission, we want to keep tracking, different regional, national, and international freight movements between locations. And as we know that actually in the U.S. and the U.S. Department of Transportation, the Federal Highway Administration has a well-known program called FAF, which actually keep tracking those annual and then about total trade for all kinds of commodities, across the region and also internationally. So here in the figure, as you can see, this is a 5-year, survey. For example, we can see that the total trade for all commodity, for the U.S. It's over $3,000 billion, and we can see that the top regions about the international, trade, from East Asia, from Europe, and also from Canada. And we're zooming to, state level on the right hand, and for specific type of food, you can see the meats and seafoods. The top, flow movers are California, Texas, Florida, Illinois, and so on and so forth. So you can see that, by understanding the food flow and also the supply networks, you can understand that the catchment of the foods. And because of concern of food security and then the importance of resilient food supply chain networks. And this is why we want to understand the resilience specifically in this work. And first of all, we want to have different kinds of measurements about the food supply network resilience. And as we know that in the whole food supply chain, it actually involves different kinds of stakeholders ranging from manufacturing, farming, packing, transportation, market share, and others. And in this work, the reason we want to utilize the geospatial knowledge graph is because that's using the GeoKG, we can first of all to represent different entities and then the relationships in the localized setting. And also using the knowledge graph, we can support the knowledge, discovery and semantic reasoning. And this is hope to better understanding, especially not only the regular pattern, but also the impacts under disruptions, such as the past COVID-19 pandemic, and also the natural disaster disruptions, such as maybe hurricanes, flooding, and so on, for the food supply. And because my research previously was mainly focused on spatial networks, so here I want to show you one figure about the importance of the network structure in those kind of resilience measures. For example, these are the two extreme representation of the various kinds of network. If we utilize the ring network structure, this is the most resilient network structure, because no matter you cut off any or remove any node in this network, so you will still have other nodes will still have a high degree of connection to others, so which is actually highly resilient. But regarding the information or the actual stuff transportation is less efficient. So the most efficient network is the network on the right hand. That is most of or many traditional internet about the star network. So we only have a big hub, and then this is the most efficient because we only have one connection to all those distributed nodes. However, this kind of network is least resilient, because if we remove the center node, and then all the connection around those distributed nodes will be disrupted. So this is why in the real network for various kinds of things, no matter it's mobility, regarding information communication, like also the food transportation, it's a trade-off between the resilience and then the efficiency. So this is why we want to understand in realistic how resilient of a specific food supply network is, using this kind of measurement and also other analysis. So back into the food supply network, that is our focus in today's talk. And there are various kind of considerations, such as we want to consider whether a regional food system is based on multiple supplier or customers, and whether it is only in supply for certain types of food, such as meat, seafoods, or various kinds of food types. and like vegetables and so on and so forth. And we also want to know from geography perspective whether the supply are from the nearby regions or from distant region or even from international imports, and also what are their monetary value distribution. So those are the dimensions or the various kind of attributes we need to consider when we do the resilience computation or analysis. So here, this is our GeoKG ontology design. On one hand, the goal is we want to utilize ontology which is both human readable and also machine readable. So this is why we want to incorporate knowledge graph. Here, I just want to highlight some of the the geospatial components first of all, because each region using, for example, the recent NS-funded NOAA knowledge graph from my advisor Christoph Janowicz. They have those NOAA knowledge graph and have a various kind of definition and representation about region and geospatial relations. And you can actually, the goal is actually, no matter what you develop here, it's not a silo. It can be automatically linked to other existing ontologies and also the linked data on the semantic web. So which is machine readable and also human readable, because yeah, as you can see, we understand region, we also understand flow, we understand like geography, manage and the monetary value. And also for the food part, for the categorization, we use two standardized classification codes. So one is from the standardized classification of transported goods, the other is from the North American industry classification systems, the English code, which is also well known for a lot of POI research. And the other important ontology we use is food done. So this is also well-known, ontology in the food system, which actually link different food products to, for example, the nutrition, which is very important for the health. So in other words, for example, if you understand like disruption of certain grocery stores or food supply chain, and you might be actually have an indication to regional health as well. So before I introduce the measure, I just want to give you a concrete example. So this is from the US Department of Transportation, the data source I mentioned earlier. For example, this is for the meat and seafood supply in the state of Wisconsin. And you can see that, okay, by the states, we have a large supply, and from, Illinois, I think mostly from Chicago airport, and also from Minnesota, and there are, nearby regions. And regarding the transportation mode, we have the underground truck transportation for our food, which is the most, used transportation mode. And in this case, we think actually regarding the state of Wisconsin, actually we are actually highly resilient because we actually rely on those nearby states will less impact, for example, for the hurricane impact like in Georgia. But because we rely on more nearby things, and also, and this is just one dimension. And back into the measure, as I mentioned, based on the geospatial knowledge graph, we have the geospatial representation of region locations. We also have those food codes like categories. So one simple thing you can consider is in this hierarchical tree of the classification of the food system. If you have a region like, okay, maybe we don't have a supply for pork, but we have a supplement, similar category, like we have the maybe beef, then this region actually are more resilient. Even without the supply of pork, we still have this similar category under the meat and seafood, right? We still have beef and so on and so forth. So this is why we can utilize various kind of semantics in this GeoKG and to support our computation of the resilience. So here, due to time limits, I will not go through the detail, but here we use entropy-based measurement to compute the resilience. And then we can, using summation of different kinds of measure and get the, also the network resilience, which means that we want to compute the most influential importer or exporter in this, food supply network. So, by building those infrastructure, we can also support like machine-based queries such as the Sparkle, and we can understand, for example, okay, what are the most resilient nodes in this food supply networks. And as you can expect, the most important state in the United States regarding food supply are like California, Texas, Florida, and so on. And this is just a further case study. We utilize those community food survey data, the CEFS data from U.S. Census Bureau, and focused on the food types listed here. And we want to understand, using the measure we proposed, and to understand the state level food supply network resilience for across the U.S. at the state level. And after finish this entropy-based study, we also face some challenges. There are the three aspects that we found. First of all, the entropy-based measures, they kind of lack some of the general reliability, so which is not stable to handle noise or missing data, because as you can imagine, a lot of supply chain, they may not have a sufficient data or complete metadata shared with the agencies. And second is the scalability issue. We have a new type of data, we actually need to redesign our ontology. And lastly, the entropy-based method requires a centralized data set. So this is why in the follow-up work, to address the three challenges, we propose the AI solution, which is a federated learning system for edge-enhanced graph neural network. First of all, using federated learning to address the centralized data issue, so to cover privacy-preserving decentralized architecture. Second, we utilize the graph neural network to address some of the missing data or noise issue to increase the generalizability of our framework. So this is a graph to demonstrate our architecture of the federated learning edge-enhanced, the GNN. And as you can see, actually, this is not fake data; it's a real data. And we, this is, for example, by dividing the U.S. based on the U.S. Bureau versus kind of schema, we can, divide into the, for example, the 4 regions, and then you can see that 3 sub-region actually has a distinct, network structure. For example, in the southern region and the Midwest actually have more, connections, regarding the food supply, which is, you will find that also in previous map, they actually are most resilient from the ground transportation. And the key idea here is that we want to utilize such a decentralized, measure. So if we do not know, for example, the information exchange between sub-regions, how can we still understand the resilience of the federal level, food supply network? So here is, the difference. For example, on the map showing the difference between the entropy-based method using, the silo data for the 4 sub-regions versus if we have the, information communication between sub-regions. So there is some actually difference, especially we can see the either dark red or dark blue. Those are the, most of the gaps. So the goal is using the edge enhanced GNN. We hope that, this kind of, deep learning structure can understand those, missing pieces and, such that we can improve the, resilience estimation. So in this network, actually, we use several, data augmentation techniques regarding like adding, modifying, and removing. So basically to, change the structure of those original food supply networks such that we can, the learning process can also understanding those noise information. And so this is some of the results we got from the proposed federated learning-based framework, and compare with the previous introduced entropy-based method. Also, we try different training strategies like centralized training or federated learning-based training, and we found that actually the Pearson correlation or some of the experiments or concordance measure actually for the centralized training is good, but some of the federated learning measure are also very close, but still has some of the discrepancies, which as expected because there is no information, exchange between those silos. But the most, interesting thing is that the robustness, when we have a missing data, for example, we have a missing maybe monetary value report, or we have a missing transportation mileage, reported from those companies, or the vehicle sensors, and we found that using those like the graph neural network learning, we actually have a relatively robust resilience estimation. So when we have such missing data. So in summary, in this presentation, I demonstrate that the importance of using the geospatial knowledge graph in representing the food supply networks, which is one type of the spatial network. And we also demonstrate the robustness of our proposed method in measuring the geospatial network resilience. And also using this privacy preserving federated learning, we are able to recover some of the global information when only the local view is available. So this is very important because we use federated data as an example. However, you can imagine in real world food supply chain, actually a lot of company organization, they do not, because privacy was a market concern, they do not willing to share the data even with the federal agency. This is why, we want to propose some privacy preserving infrastructure such that maybe we can still get some, global information, even the individual silos are, existed. So future work, we also want to try more such as, natural language description, processing technique to those automatic extraction, entity matching with the GeoKG. So with that, yeah, thank you all for your attention. So now I'm open to question and comments.
Thank you very much for your presentation. So we now see a question from the chat. So Ryan, do you mind to okay, let me see the current we would like to connect about we have some co-interest on the. Okay, so this is not a question, but is there any question from the audience? Yeah. Okay, that's a comment. Sorry.
Yeah, thank you, Ryan.
Mm-hmm. Anyone who has question can feel free to, ask directly. Okay.
David Page here at Oak Ridge. So thank you for that. It's a very interesting presentation. So just for my own interest, what kind of computational requirements were necessary to train up the networks? And was it, did you need HPC high performance computing, or was it something you could do on a desktop? What was kind of the requirements for computation?
Yeah, thank you, David. So in our case study, actually, the data is not that huge. So yes, we just train in our, just one, regular, Linux server. So in this, setting. However, yeah, I can talk a little bit about our future. This is why we hope to, move this computation. This is more like the pilot study, and then we hope that we can, host it in our, like the intelligent cyber infrastructure and in the institute, and such that we can, for example, provide maybe APIs. And we actually we have meeting with the DOT and FF agency, and we are thinking, because they are already published data tables and so on, but they do not have those like the resilience measure. So one thing we can do is for example, we can do the maybe computation, training, and so forth on our cyber infrastructure, and then we can provide this as the API. And also, they do not need to share data because we want to, doing like privacy preserving way.
Yeah, we have two more questions from the chat. So, Phil, do you mind to directly ask, or you want me to ask it?
Sure, yeah, I can ask from here. It's a great talk, Dr. Gao. I have a question regarding when you deal with the different regions. Obviously, as you said, they have heterogeneity across different states or different granular units. So how do you deal with that kind of heterogeneity within the GNN model, or it's been taken care of automatically in the graph neural network?
Yeah, thank you. Yeah, Dr. Yang, this is a great question. So currently, this kind of heterogeneity has been taken care of by the GNN, structure. However, there is one setting we can modify. That is, for example, we in the federated learning we can use like federated average or federated optimization or federated Bayesian, learning. So I think this part, if we want to consider such, spatial heterogeneity, we can modify, for example, the federated average, component into others. So I think that's actually, is actually very interesting research direction.
Thank you.
Very good. Hi, Hansen, do you mind to directly ask, or you want me to ask the question from you? So, okay, so let me ask. So why did you use the state instead of the FAF zone geographic units? So, and also most movement of the food happens within the state or within the FAF zone. Is this the model only looking at the interstate flow?
Yeah, thank you. Yeah, Hansen. So, first of all, actually, although I only shoot the the analysis at the state level, but the framework can also be applied, to the large metropolitan area. Yeah, so from the same ESF data source, and we consider both the interstate as well as the within state flow. So you can see there is a self connection. So in our diagram, yes, we do consider both.
Okay, thank you very much. Hi, Gengchen, do you mind to ask directly?
Hi, Song. I just have a question for the first part. When you discuss about the related the measures. So do you implement a function in the Sparkle to automatically compute that, or this is like a separate functions after it gets the query results?
Yeah, thank you, Genshin. This is also a great question. So as we know that there is a trade-off between the on-the-fly computation versus pre-compute function. So in our existing study, we use the server-based computation. Is a pre-computed. So which means that we have in the Spark query, it's more basically more efficient to return the result, but we envision that we cannot pre-compute every measure. So this is why we are also thinking about whether we can have those architecture that can maybe automatically define those functionality on the fly just based on the input ontology. So I think that would be actually a very interesting development area.
Okay, thank you very much. Seems the time is also perfect.
Okay,
thank you again for your presentation and the question of our next keynote speaker, Dr. David Page. So he is currently a senior, currently a senior research and development staff and the section head of the Oak Ridge National Lab. So his current research involves advanced 3D and stereo reconstructions algorithms with an emphasis on the high-performance computing algorithms. Okay, so he has a strong synergy of academic and industrial backgrounds, which helps him to uniquely position to handle those toughest HPC imaging challenges around the country. So he has won a lot of awards in academia and industry, such as National Innovation Award. Because there are a lot of awards from him, I cannot enumerate all of them. So his talk name is High Performance Computing, Image Processing, and Digital Twins at Oak Ridge National Lab. Let's welcome him to present. Okay, thank you.
Thank you. Hopefully my audio is okay.
Yeah, everything is okay. I can also see your screen currently.
Perfect. Thank you, Dr. Thanks for that great introduction. I hopefully I'll live up to it. So thank you for inviting me. This talk is a little bit more high level. It's not necessarily an academic talk. It's more focused on what my hope is that through this talk, you will take away the value of geospatial digital twins and why there's this paradigm shift to move toward them, and then why HPC, high performance computing, should be a part of that role. And then, I'm going to try to weave in the AI components. About 18 months ago, we at Oak Ridge started seeing digital twins as kind of something that we needed to put our eyes on and understand what they were. And through that, myself, many of you may know Dr. Budu Baduri. He's my boss. He's my division director, well known in population dynamics and population modeling. And then my colleague, Carter Christopher, and I, the three of us started trying to do a deep dive on what is a digital twin. And this talk kind of evolves from that. We use this talk to educate our staff, and then also to talk to partners as to what is a digital twin, why is it important. So hopefully that you'll be able to pull from the talk those things. So one of the key motivating factors, this again is not my work, but this is some work that illustrates, I think, the value of a digital twin, which is currently today, a lot of geospatial and GIS products are static maps. And the value of a digital twin is to be able to model things not only spatially, but temporally. And this gives a good example of if you're trying to model streams on a map, they're just a line. But what we would really like to do is give a user that's looking at that map a notion of what state that stream is in, what the water level is. If it's a temporal feature, give temporal information so that when you encounter that stream, you know that day what to expect from a water level, not just a min and a max or bounded, but to give that day what's possible. And so a more realistic example of this is something we're probably all familiar with, or at least I am when I'm traveling with my family, which is using Waze or these traffic management tools. In essence, these are digital twins. Waze is a very good example. Now, the base map of Waze is static. It's not changing. It's not a digital twin. It's not dynamic. But the traffic models inside Waze are, in essence, a digital twin. You're using. There's some terms I'm going to start using that will hopefully come out through the talk. One is a digital thread. There's a digital thread from your iPhone back to the Waze servers. The Waze servers are collecting all sorts of individual iPhone movements to be able to build up traffic models. And what that allows you to do is do real-time routing of your vehicle so that again, base map's not changing, but the traffic model is. That's the big value of the digital twin. And then another thing is something called twinning rates. The twinning rate, how fast that model is being updated, is seconds with the Waze. Back in the 1990s and 2000s, I used to use MapQuest. I don't know if anybody's familiar with MapQuest, but MapQuest also had routing capability, and but it was the twinning rate for MapQuest was probably weeks and months. They were scraping Department of Transportation construction zone information that was likely out of date when I actually traveled. So it's not a very good digital twin, but Waze is. And that's the promise that we can get after with digital twins, is that we can have these real-time, up-to-the-date temporal features being modeled and being put out for predictive analytics. So at Oak Ridge, really we're kind of tied to the paradigm of the computing infrastructure and the computing fabric that we've been using. Turns out that when GIS and geospatial really flourished and took off was in the 80s. Prior to that, mainframe computers were used for GIS, but in the 1980s is the decade of the PC, the personal computer, and Esri really kind of ported everything to be on the personal computer platform. Very smart move. We would not probably have the geospatial capabilities that we have today if we weren't inside that personal computer footprint. The downside to that is now that we have really escalated GIS spatial capability, we're kind of locked into that PC framework. All of our geospatial workflows sit within, they don't necessarily sit on a PC, but they follow that PC pipeline, and it has limited us into kind of emerging into this digital twin world. At Oak Ridge, I don't want to make this too much of a statement, but this is a picture that shows Dr. Baduri there on the left and some other colleagues. This is around 2005. Our division sits right on top of the big iron, the big computers at Oak Ridge. Our offices are above it. And in the early days of the supercomputing, Boodoo had a side hallway conversation with one of the implementers of the supercomputers. And that hallway conversation was very informative to say, hey, what if we start moving geospatial out of this PC paradigm and into high performance computing? And that led to a lot of the work that, if you're familiar with Boodoo's work in R&D, it's called Landscan. I would argue that we're a little bit behind the times as far as a digital twin goes with Landscan, but that was kind of an early push of pulling high performance computing in and building these digital threads to model things automatically to build out products. So I don't want to overemphasize that, but we've always at Oak Ridge been working in these HPC environments, and I think that gives us a good viewpoint as to why we want to move into digital twins. And this next slide deck kind of motivates that. We're really talking about a paradigm shift. The traditional geospatial workflow looks something like this, and USGS and your geospatial organizations tend to be organized like this, although USGS has been very good at moving away from these pipelines. But you have some product at the end that you're trying to generate, a map, a vector map, or whatever, and then you flow through a sequence of steps to get to that by defining the requirements that you need, collect the data that you need, process that data, analyze it, perform QA, QC, and then finally at the end, you stamp out the product, you stamp out the map, you stamp out your whatever it is you're delivering to someone that's a GIS product. And unfortunately, due to memory limitations on PCs, due to memory, just the workflow natures, the value never really comes till the end of the stage. That end step is where all the value gets packed in, and any interim data steps in that process kind of get thrown away. They become very ephemeral, and so we end up stovepiping on this workflow. So if you're creating terrain data, which is what I'm doing, or you're creating building models, those two workflows will have very different pipelines, and they won't share data between them. They could. There's lots of good data that can be shared, but because of the nature of the workflows being built, particularly inside organizations, that data gets dumped on the ground. And then more importantly, if you have a change at the end, it's very difficult to have an agile product cycle, because if you change the product specifications, you got to go all the way back through the pipeline. And a good example of that is in terrain is the SRTM data. Maybe some of you all are familiar with this data, but it's a very popular data set to be used in geospatial, particularly for doing geolocation or other type things underneath an image. But the SRTM is what I would argue is a model. It is not a digital twin. The data that was collected in the 1999-2000 timeframe, and although there's been different releases over time, they're just improvements on that original data. So if you talk about twinning rates, it's like there's no twinning rate. No new data has really been collected for SRTM. And if it is, you want to talk about decadal type twinning rates, very slow. Australia has probably moved a couple of centimeters, if not meters, since this data was collected. I don't want to say it's out of date, but the continental drifts and things are changing such that this terrain model has some wear and tear on it since it was collected in 1999. And so there's almost no digital threads that go from the raw shuttle mission collect to create these DSMs. It's a very manual process to create it. And so what I'm arguing in the paradigm shift that we need to move toward is get out of thinking about the products that we need. Those are an end stage, an end step, and start thinking about the value in a model that is trying to mirror the physical world. And I'll talk a little bit more about this soon, but for example, in the digital terrain modeling or digital elevation modeling, rather than our value being in a DSM, our value's in a point cloud or a train mesh that's an intermediate step. That's where that green box is. And what our teams at Oak Ridge and other partners are trying to do are to build these green threads, automated, no person in the loop, to go from a measurement of the physical world to a model of that physical world in a virtual space. And then more importantly, also creating those digital threads to go back from the virtual world to the physical entity. And so you can think about that in terms of ways. Your iPhone is kind of the sensor that is collecting the physical entity. You've got a digital thread that's pushing all your motion data back to a central server. And then there's another digital thread that's pushing traffic, aggregated traffic data from all the iPhones back to your phone so that you can make traffic management decisions. Those are the kind of things that we got to start thinking about with digital twins. And importantly, HPC, high performance computing, I would argue, is going to be the tool to help us get there, as well as AI. I haven't focused a lot on AI, but AI is going to be a central capability there if we want to automate these processes. So this is just one example of a digital twin that we're working on. And we want one other argument I want to make, and I'll make this again at the end, is that you don't want to build a digital twin that solves everybody's problems. If you try to solve everyone's problems with one digital twin, you're never going to make progress. I would argue that we're going to have several different types of geospatial digital twins focused in certain areas, and those will branch out and solve other things. And again, I'll talk about that at the end. But in this case, our focus was to build a 3D terrain digital twin. So what we focused on is we're right now focused on EO, electrical optical imagery. So there's tons of commercial satellite imagery collecting daily across the globe. It's overwhelming how much imagery is out there. We have built automated tools that go and query the commercial tool sets, identifies stereo pairs, either collected as stereo or fortuitously collected. We can find overlapping in their databases. We automatically can pull that data and then run it through our stereo algorithms to reconstruct 3D point clouds. So our virtual model that we're building is a 3D point cloud of the Earth that's constantly evolving. Anytime we get new data, we populate it into the point cloud. And we don't worry about the products that we're delivering to people. That's a stage that is easily automated. It used to be that you worried about the kind of map you were delivering, but translating from a point cloud to a DSM, or a point cloud to a mesh, or a point cloud to a GeoTIFF, whatever product somebody needs is, we have a partner that we work with that has a really nice suite of tools that can automatically stamp this point cloud out to whatever products are needed. So we stopped worrying about the delivery of a product, and we focus on building these fast digital twinning rates to keep our point cloud up to date. And that's taking HPC, if you know anything about stereo algorithms, working on satellite imagery, those matching algorithms take a lot of computation. And then at the scale of the globe, that can be a pretty heavy lift. And we're looking at resolutions higher than the SRTM, a couple of meters rather than the 30 meters that SRTM's at. Okay, so if you kind of stayed with me, you start to see the value of HPC and high performance computing. But there's some things that we would argue that you need to think about in terms of a digital twin. At Oak Ridge, we've got a great resource in our supercomputing, but we really also have a lot of resources in on-premises HPC, meaning that we have built some special high-performance computing stacks tuned to specific problems. Weather is an example. We have a specific stack that's built for weather modeling. And then we also have good capability to surge into AWS, into the cloud, when needed. So I would argue that you need to think about your digital twin, and if it's something that can sit in the cloud and you can afford that, that's one option. If you really have the resources and want to build an on-premises, you can build an on-premises HPC. A lot of our funding partners prefer that because they can control it. but you do need to think about, where you want to build out your model. The second thing you need to think about is where your data is going to reside. That may drive the type of HPC you're going to do as well. It's very expensive to move the large geospatial data around. If you've got, for example, if you're working with Sentinel data, which is a remote sensing data set, some of that already sits on AWS. It can be very costly to move that data down to your own HPC fabric to run on. So you need to think about where your data resides and how you're going to move it around to be able to build out the digital twin that you want to do. And so part of this deep dive into digital twin for us, we kind of went back to understand why there was an interest in this and who had done it first. Well, Geospatial is kind of late to the game on this, but I think that's always good to be a fast follower rather than someone chopping all the weeds down. If you go back, there's an interesting book in 1993 by Geltner that talks about mirror worlds. There's not a lot of meat in this book that you can really pull out, but it does give you inspiration as to, he had a good insight that he could see that computing, sensors, and everything would get to the point that we would be able to build these digital twins, what he called mirror worlds, and his hope was we'd put them in a shoebox. I'm not quite sure we're in that stage yet, but it's a very inspirational look at how to get to digital twins. And then, of course, industry has really adopted this, particularly manufacturing and the oil industry. There's an influential paper in 2003 motivating why offshore oil rigs and the oil industry would want to move into digital twins. And then 2012, an influential paper from NASA really started making the argument of why digital twins are where many industries need to start moving. NASA has always had what I would call physical twins. If you've ever seen the movie Apollo 13 or read any of the history of NASA, you know that any ship, any craft that goes into space, they have this physical twin on Earth that they can run through engineering solutions and then radio communicate those up to the crew. And that was very instrumental in the Apollo 13. The 2012 book argues, if physical twins are nice, but if you also have a digital twin, bytes are cheaper to copy than bits. Bits and bytes are easier to copy than atoms. So you can run multiple scenarios on a digital twin and evaluate different projections is what you want to try to do with something. And so that's the value that NASA sees out of digital twins. The Smart City Initiative is kind of a good initiative to follow for geospatial. There's a 2017 paper that started looking into this. I haven't followed this the way that I should, but my initial impressions is that smart city initiatives and digital twinning have not quite met the hope and the promise that you would like to see. I'm not sure why that is. I'm speculating as to why. I think some of the why is that clearly the sensor infrastructure is there. There's a lot of building infrastructure, a lot of traffic infrastructure. I think that municipalities may be struggling to get the high performance computing and the storage resources necessary to truly build out a digital twin. And then I'm also suspicious that just regulatory concerns that private companies sharing data with public entities may be also a heavier lift than most people anticipated. But I think it's important for geospatial to keep an eye on the smart city initiatives. There's Singapore and another German city have made some pretty good progress with it. And some of the companies from NVIDIA and maybe even Esri that are looking at digital twin products are starting to team up and work with them. So something to keep a good eye on. And then in terms of AI, I think AI is going to be an enabler for building out the digital threads that are necessary to model the physical world. But more importantly, if we have a good virtual model, it's really the next stage of artificial intelligence to be able to run scenarios on that model. And it really just evolves the evolution to, I think it's potentially one of the final steps of what we as humans do in terms of intelligence. And this chart kind of illustrates that. If you look at how we think and do things, in the 1970s, 1980s, expert systems became kind of the thing for artificial intelligence. And they really revolutionized, the if-then kind of approach to solving problems. And TurboTax is a good example of that. If you've got a problem like TurboTax, the expert systems are very good at kind of weeding down your solution space. And then, in the 90s and 2000s, Bayesian networks, causal inferencing really started to take hold and gave us another solution step to be able to attack human-like intelligence at some level. And spam filters are the good illustration here. We really saw in 2000 spam filters becoming very useful once you applied these causal inference models. And then everyone is probably aware of the 2012 deep learning revolution that we've really gotten now where we can have computers to draw decision boundaries in very similar ways and even better than humans would draw those decision boundaries, which is really a big enabler on our terrain data and big enabler on building a digital thread to model the world through remote sensing imagery. Particularly, we've got a lot of initiatives to get building footprints and building heights, and we'll use AI/ML algorithms at Oak Ridge to extract building footprints, and then we'll use our terrain models to actually add elevation to those. And then that informs, if anybody's aware of Boodoo's work, we use those building footprints and building heights as proxies for our population distributions. So all this kind of wraps together, which is the other big value of digital twins, is that when you break, and we do this a lot at Oak Ridge, when you break out of that PC traditional geospatial pipeline, you end up sharing data across all your different products, which in our case are, I don't want to oversell this, but we would start saying we're creating these digital twins from population estimates, terrain modeling, to feature extractions. And then finally, if you do have a good digital twin, you can start overlaying physics models onto that digital twin and doing predictive analytics. This is the big promise I think we can get after. With our terrain model, we have not done this work yet, but there are researchers at Oak Ridge that are very good and experts in hydrography, and we really want to start bringing in hydrography so we can get after that stream problem at the beginning. If we have a very high resolution terrain model, we have good sensors about the weather, and we have a good hydrography model, we should be able to predict at a very high rate, hourly, up to the minute, stream levels to be able to provide to users so that just like Waze, knowing the traffic levels, when someone approaches a stream, a lake, or some other area, they can know what water levels to expect, what the moisture content of the soil can be to help drive whether you can traverse that terrain or not. Now, if I'm doing okay on time, I think I've got 2 more minutes. Let me wrap up. There are some differences between the industrial digital twins. One is we have a lot of nonlinear coordinate systems. That bites us a lot in the work I do, something to be aware of. We can't go everywhere, and it's going to take cross-disciplinary teams. I want to wrap up and end with this slide to say, I really want to argue that when you build a digital twin, you don't want to build one that solves everybody's problem. If you do, you'll end up building something like the space shuttle. I taught at Space Camp. I love the space shuttle, but the reality is it was a terrible solution. 135 missions and 2 total failures. And the reason is it was trying to satisfy DoD, DOE, NASA. It tried to solve everybody's launch problems, and it ended up solving no one's. And I think that's what can happen with a digital twin. And I think the other way to approach it is the curb in the road. We've got a very nice solution for handicap access where we put these little curves, very nice, simple solution in the road, and it makes handicap access great, but everybody uses it. My wife and I use it when we stroll our daughter in a stroller. The beer man, Bud man, when he's got a heavy load of beer and he's got it on a trolley, he uses that. And the same thing happens with Waze. Waze started out very good traffic management, but everybody uses it for estimated time arrival, to find gas stations. It branches out in other ways. So I've gone way over my time, but hopefully that motivates why we want to go to digital twins. Thank you.
Thank you very much for your nice presentation. So now we are looking forward to the questions from the audience. So we can have 4 minutes to have questions and answers if there is any questions.
Dr. Page, thank you for the great talk. In fact, from the computing perspective to see how the digital twin may or may not work, that's very eye-opening for us. You mentioned that's echoing also from different domain talk about digital twins. We should not build a digital twin that works for everyone, like the last one, the shadow example. So could you comment on what kind of granular we should set the scope for digital twins so that it becomes mostly as a success instead of a failure?
Yeah, it's a great point. And I don't have a crystal ball to answer that well, other than I can give some experience. On our digital twin that we're trying to build for terrain, one of the things that we've run into is that what resolution do we want to model at? We could go down to the submicron level, right, and have a very dense point cloud. We've since decided that, for most conditions, you want to be, in the meter type range, that you go below that and it's going to be hard to model and it may not be useful. And if you go into that submicron range, you're going to require so much storage, particularly for point clouds, that you're not going to be able to maintain your digital twin. So you do need to make resource judgments as well as I know that's not the specifics of your question, but resource judgments are one driving constraint. The really big constraint is, I would argue, that traditional geospatial workflow that we talk about, there were some specific products we were trying to generate. I think that's a good starting point, is to start with, there is a need for something you're trying to do. What is it you need? Why do you need it? And to focus on generating a digital twin to deliver that capability. And I think that's the granularity to start with something you've been doing, but maybe using a traditional workflow to get to it, and then build a digital twin because there's value at the end. And the goal is to push the value back into the chain a little bit more, so that all the ephemeral products you're generating, for example, on our Landscan project, where our value is in the population models, we actually generate a lot of data, points of interest data. We generate building footprint models, several things back in the stage. And so we focused on building Landscan, but as we went back and pushed things back on the HPC platforms, we've now spun out other digital twins for points of interest. We have a digital twin at Oak Ridge, runs every day and maintains a large geospatial footprint of points of interest around the globe based on volunteer geographic information. So I would argue, focus on your end state and then build a digital twin backwards, because there's some value there at the end, and that's what I would suggest.
Okay. Thank you very much for your answer. We have two panelists. One is Dr. Gengchen Mai, and the other is Douglas Rao. So our procedure is the following. So basically, we start from the short talks from our panelists, one by one, and each gonna take around 10 minutes. And after that, we're gonna have a panel discussion of around 30 to 40 minutes. So let's first welcome our first panelist, Dr. Gengchen Mai. So I will first give a very short, brief bio of him. So he is an assistant professor at the Department of Geography of University of Georgia. And he was a postdoc at Stanford University. And he has strong joint expertise on geo and also machine learning. And actually, he is one of the pioneer researchers of foundation models for geo data. And it's our pleasure to listen to his recent work and opinion about the current stage and the promise of foundation models for digital twins and the geoscience, etc. So let's welcome the talk from Dr. Mai. Okay.
Thank you for Professor Liang Zhao's great introduction. Let me just share my screen. Can you see my screen?
Yes.
Hello, everyone. This is Gengchen Mai. I'm currently an assistant professor at UC Geography. And it's my great pleasure to give a short presentation at this digital twin digital twin webinar. So today my presentation is about a self-supervised contrastive spatial pre-training method for geovisual representation learnings. But this is the aim is whether we want to build a self-supervised objective for building a multimodal foundation model for GeoAI. So low data or few shot regime is a preliminary, a very important or significant challenge in the geospatial domain. So we usually have access to massive amount of unlabeled geotech data. So where labeled data are rather scarce and expensive to collect. So for example, we have multiple satellite continuous captures remote sensing images with corresponding geocoordinates all over the world, which lead to a large quantity of unlabeled geotagged remote sensing images. So similarly, users in Flickr's, Google Photos, Maplers, and Naturalist app upload millions of geotagged images every day. The images about species, the neighborhood, or for sightseeing. So this geotagged unlabeled data are inexpensive to obtain. In contrast, the desired labels for many geospatial tasks, such as object class labels, bounding box, and land use type labels, are rather scarce and expensive to collect. And they rather have imbalanced geographic coverage and potentially oversimplified label distributions. So here, I show two examples. So the left figure illustrates the geographic coverage of a labeled satellite images and street view image dataset for 15 benchmark datasets from our certain band dataset. So you can see the geographic coverage is very unbalanced. The right figure shows the geographic coverage of one of the widely used species fungi recognition dataset called NOAA bird. So we can see that the geographic coverage of this dataset are very balanced, and this is very common in a lot of the dataset we are using to benchmark our AI models. So these restricted label dataset problems severely limited the abilities for model generalizations. So our proposal is, instead of only supervised trained on labeled geospatial images, we want to build a multimodal self-supervised learning framework between the geolocations and the images on the massive unlabeled geotagged images. So more concretely, the idea is we want to contrast the representations between images and their corresponding geolocations in a self-supervised manner. So the advantages is that this objective can help the AI models to learn knowledge from two complementary domains. And the whole architecture becomes geo-aware and can perform implicit spatial reasoning. So before to introduce our contrastive spatial pre-training framework, there are mainly two mainstream approaches to fuse geographic knowledge into say image classification model or other AI models. So the first set of work is illustrated in this figure. So the idea is to supervise train, say, image encoder and the location encoder separately, and then we want to combine their predictions. So we call this a super-only approach, where the drawbacks is they can only leverage the labeled data, while just disregard all the massive unlabeled data. So to utilize the massive unlabeled data, there are many previous or pioneer research explore the possibilities to doing self-supervised learning or unsupervised learning on unlabeled geotag images. However, the general idea is to SSL pre-training on image encoder, and many of the models utilize the geolocations as accelerated informations to build up this SSL loss. So for example, the well-known Tell2Vec papers, they pre-train the image encoder with an unsupervised triplet loss, while the embeddings of spatially nearby satellite images are more similar than those of the distance tells. So another example is a GeoSSL model and a seasonal contrast model. So they pre-train the image encoder with a geo-aware contrastive loss. So they use locations as accelerated informations to generate a spatial aligned remote sensing images at different timestamps at positive samples. So another example is GeoKR framework, which pre-train the image encoder in the teacher-student network by minimizing the KL divergence, KL loss between the image representations and the spatially aligned land cover maps. However, you may notice that all of these models, they only use geolocations as auxiliary information in the SSL pre-training. But after the pre-training, all the location, all the geographic informations, what we call is location information, is completely ignored during the model fine-tuning and inference stage, which lead to significantly suboptimal results. So how to solve that? So unlike all this previous approach, we propose a contrasted spatial pre-training model. So the CSP use a dual encoder framework, like very recent, very popular image text pre-training model like CLIP and Align, which is also a very famous multimodal foundation models. So in the SSL pre-training stage, we do contrastive learning between the image representations and location representations. So after the SSL pre-training, so both the image encoder and location encoder will be fine-tuned and used jointly in the inference stage. So by doing that, we can absorb the advantages from both of two previous methods, but avoid their drawbacks. But how do we set up the contrastive pre-training stage? So we actually explore a combination of 3 different ways to form positive and negative pairs for the contrastive learning. So the first one is in-batch negative sampling, which is very similar to many multimodal foundation model contrastive learning method. So basically, give a mini batch of unlabeled location image pairs. We create a mismatching location image pairs as negative samples. So another sampling is random negative location sampling, which is also widely used in several like GeoAI applications, such as we just uniformly sample some negative locations from the study area to form the negative pairs. The third one, the third approach is the SIM-CSE-based sampling. So basically, we create a positive pair by encoding the same locations with 2 location encoding towers, which share all parameters but use different dropout masks. So basically, we may want to make the model, the location to this dropout approach. So in order to evaluate the effectiveness of CSP, we actually test on two GeoAI image classification tasks. One is the fine grained species recommendations, one is satellite image scene classifications. So, but in order to demonstrate the effectiveness of this pre-training framework, we pre-train the whole we pre-train the model on the whole unlabeled geotagged image dataset, but we only fine-tune the model on a subset of the training data, like by using different ratios. For example, only train on 5%, only fine-tune on 5% of the dataset, or 10%, or 20%, or 100%. So experiment result on this 2 data sets show that our CSP can improve model performance on both tasks under different label training data sampling ratios. So especially on the naturalist fine grained species recognition dataset, we found out our model can improve the model performance with 10 to 34% relative improvement. So to learn why this model is effectiveness, we actually do a series of ablation studies. So first, the ablation study is tried different SSL pre-training objectives. So we find out that, okay, for all these 3 negative sampling methods, combination of them yields a better performance. If we deleting one of them, this leads to model degradations. And the second ablation study is we try the different location embedding dimensions, and we find out the location embedding to 256 lead to the best future learning performance. And third is whether our CSP models is effectiveness on different image encoder. We try 2 options: assumption V3, which is a more CM-based model, and the vision transformer. We find out no matter which image encoder you use, the CSP is always an effective model to pick. So our proposed CSP models is a generalized geospatial self-supervised learning framework. It can inform a new ways to develop geospatial foundation models. So in fact, until now, there are many foundation models available, such as ChatGPT, Segment Anything, and ImageGen. However, none of them is powerful enough to support many GeoAI tasks. The reason is most of these foundation models is only focused on the commonly used data modalities such as text, image, videos, and audios. However, for GeoAI tasks, there are many unique data modalities such as geospatial vector data, trajectory data, raster, remote sensing images, street view images, geospatial knowledge graph, and so on and so forth. Especially for geospatial vector data, as far as we know, there is no existing foundation model which can handle that. So in order to handle this, a bunch of data modalities to make the GeoFoundation model work on various GeoAI tasks, we should develop such model. So the key is to form a good pre-training foundation model objectives. To do that, we actually can leverage the geospatial relationship as alignment between different data modalities as shown in these figures. So this is actually a generalization from our CSP framework. But instead of only contrast location and image representations, we can conduct contrast learnings among neural network representations between multiple different data modalities. So the key advantages is such a model is able to enable spatial reasoning and knowledge transfer across different data modalities. So that's all my presentations. And we also organize a special issue on IGGS about GeoFoundation models, as well as a special issue on spatially explicit AI on International Journal of Applied Earth Observation and Geoinformation. Thank you.
Thank you very much for your nice talk. Very inspiring. So we can allow one question. So Dr. Du, do you mind to directly ask?
Oh, this is Jiaxing. Yes, thank you for the great presentation. Can you elaborate on the details on the satellite image scene classification test? Because I amazed how the species image can help like satellite image scene classification. Why it works?
Oh, yeah. So essentially, I think what you are asking is it's intuitively that location will help on the species classification, but why the satellite image can help. So essentially, we are learning the label distribution. So the location representation is helping to learn how the satellite image is distributed all over the world. So, different satellite image. So the downstream task can be, say, land use classification or like object recognition. For example, okay, this is a helicopter pad. This is a harbor. This is like a park. This is like a amusement park. But all of this information, they have a prior geographic distribution. For example, the airport or the harbor will follow the coastal line. So you have to using this contrastive learning to learn these prior distributions in a hidden way, because you just learn the image feature with the location feature, so that it will have the aligned representation which help you on the downstream tasks. But I want to emphasize it's not because it's not use any labels. So the fine-tuning stage can update this representation in terms of what specific downstream task you want.
Okay, thank you.
Thank you.
Thank you.
Thank you. So yeah, go ahead. Who is speaking? Go ahead. Who is speaking?
Dr. Mai, there's a question in the chat window from. There's a question in the chat window from.
I can read the question. My mic is on. I can read the question. Hello. My mic is on. Great work, Gengchen. Hello. Hi. Great work, Gengchen. I have
It looks like there are some echoing sounds, so
it
looks like there are some echoing sounds, so if you can just respond by reading the chat window. That'll be great.
Oh, sure, yeah. So the question is, Dr. Xiao Huang is investigating how large language models interpret and understand remote sensing images. I can see the relation between the texture and visual embeddings, but I'm also noticed a huge mismatch with information and balanced between these different modalities. His question is unrelated to what you have presented, but is how we do create better and cross-modality foundation models. We're recognizing the different level of information richness, even contrasting information from those modalities. That's a very general question, but it's also a very valuable one. From what I'm seeing, so the contrastive learning is only a contrast, the general representation between the image and text. But if you want to see contrast in like more flagrant stage, say because the image contains more information, you are not only want to recognize the what's the general type of the images, but also want to learn, okay, where this object is located. But then the better way from my point of view is to do instruction fine tuning. Just as what's a GPT-4 vision. I think this is a effective way to do so. But I think for geospatial data, the most challenging thing for us, or for a lot of the foundation model development, the key is to develop well-represented data sets and tasks which interpretable and can be widely applied to a lot of domains. And this is actually a lot of development we see not only in geospatial research, but also in a lot of AI research. Yeah.
Okay. Thank you very much again for your talk and the question answer. Let's move forward to the next speaker, Dr. Douglas Rao. So he is currently a postdoc researcher in North Carolina Institute for Climate Study, and he got a PhD from the Geographical Sciences from the University of Maryland. His research background is very broad, covering the different areas of the statistical models, satellite data development, and the land atmosphere interaction, and also machine learning. So let us welcome Dr. Rao for the presentation.
Thanks for the introduction, Leon, and also thanks for the invitation. And yeah, I was a postdoc about 2 years ago, now a research scientist with the Institute. And I also saw some colleagues in the group. And I want to share a more broad community perspective on how AI machine learning that can enable digital twins. And I'm currently with the Corporate Institute for Satellite Earth Science Studies, which is one of the NOAA's corporate institute, and supporting NOAA's National Centers for Environmental Information and NOAA Center for Artificial Intelligence. And two groups I'm going to talk about today is about the Earth Science Information Partners, as well as the NOAA Center for AI. So maybe not everyone aware of the ESIP, or Earth Science Information Partners, which is a group of communities within the Earth Science data domain, which trying to bring together participants from industry, as well as government agencies and academia, to understand the value and how to maximizing the value of the Earth science data and informations to support the users to use the Earth science information to make decisions. And within the ESIP, that is really operated in a more community-driven development aspects, and there are more than 3 dozens of the groups that are working on different topics. And I highlighted a few groups that here is relevant to machine learning and digital twins, from the semantic technologies to cloud computing, and especially focused on the data part. There is also the Council of Data Facilities, Data Readiness, which is a group that I'm a co-chair of, specifically focused on the AI-ready data and how can we define a community standards on improving the data availability and usefulness for the AI machine learning development with the open environmental data. And there's also clusters like machine learning that's actually chaired by one researcher, George Mason, Ziheng Sun, on the how can we improve the practical adoption of machine learning in the geoscience domains. And groups like information quality cluster specifically focus on the data quality and the information quality. And we all know the phrase of garbage in, garbage out. A lot of times when talking about machine learning, the data quality is a key piece of the aspects we need to focus on to improve the data for machine learning development in geoscience specifically. And within the group of data readiness cluster, what we have been working on in the past 1.5 years or 2 years is really bringing the members from the community, including both agencies like the NOAA, NASA, USGS, as well as the private sectors like the IBM and other groups, and also international agencies like UK Met Office, trying to understand what's the need of machine learning and AI developers for those open geoscience data, and to understand how can we make it much more easy and more practical to use those data for AI machine learning development process. So we have developed a checklist, which is using the GitHub space to do the community engagement and management. And it's an iterative process to improve the aspects of how we can make the geoscience data more readily usable for the machine learning developments. And with that group, we are really focused on 4 aspects, trying to develop the data standards to maintain and improve the data sets, and also trying to develop automated tools for the AI readiness assessment for all those available data sets to make the targeted improvements once we have the assessment results. And the last step was really to sustain engagement with both academia, federal agencies, as well as the industry partners, because we all seeing the rapid evolution of those foundation models, and especially in weather and geosciences, has been mostly driven by researchers in the industry that have been developing a lot of those new technologies. So engagement with those active developments can be critical to really accelerate those adoptions of those foundation models and how that may be used in the digital twin space for that aspects. And that is part of the first community I want to talk about, the ESIP, which is open to anyone who want to participate. And the other group I want to mention here is the NOAA Center for Artificial Intelligence, which I'm part of a team to developing the community about. And so if you look at this QR code, you can find an NCAI's website, where the NCAI is really strive to benefit the NOAA's mission by accelerating the use of responsible AI through those coordinated development engagement with the community, including academia, private sectors, as well as partner agencies. And on the right side, you can see a recently published story map to just sampling a vast domain of the applications that NOAA has been developing to support all the aspects of NOAA's mission, from the weather forecasting to the ocean exploration and the marine protected species conservations, as well as space weather forecasting. And also that example is really great with open science spin to through the community competition, that we really enabled some of the deep learning technologies in those operational use for the space weather forecast. And through the NCAI, one of the key areas for the community engagement. So last year we did last year's NOAA AI workshop. One of the focus is on digital twins, and really focus on how can we use those data-driven solutions to enable the digital twins. And we all know that European colleagues has been really rapidly developing different technologies in the digital twin, like Destination Earth. And so we have been talking about what are the core components of digital twin, that from the foundation, which is the cyber infrastructure and the platform, as well as the information management framework. I think I saw Ryan, my colleague here in the participants, so he has been leading a lot of those interoperability frameworks, and how can that make sure all different systems can crosstalk with each other. And with digital twins, there's also the core functionality, which is the data lakes and coupling with computational modeling. So that, I believe, Ken gave a really great presentation about 2 webinars ago on the NOAA's perspective on the data systems. And on top of it, the high level is the user interface for different type of applications like decision support, data visualization, like risk communication. I really like the comments that they made earlier, like digital twin, it's not for all the users. So when we're talking about user interface, we want to be aware of what the key users we are targeting and how can we make sure those digital twin systems are useful for those specific use cases. And with the digital twin, there's also core features like the interactive nature of the system, how it between the model as well as the real ingest of the real-time data, and also the computational efficiency, which which the use case context is core. So the disaster response requirements for computational efficiency is definitely different than the climate resilience planning for the computational efficiency. And also we want to ensure the digital twin has a robust representation, as well as that we can assure the quality and ensure the users can trust those digital twin systems. And we have archived a white paper that's outline all those components and the key features that we believe a digital twin system should have. And I just want to end up with one example, is a research example that through the NOAA AI workshop, we did a hackathon about 2 years ago, really focused on how can we use those data-driven solutions to create a climate Earth system model emulators to accelerate some of those scenario plannings. And if you look at those like shared economic pathways for the CMIP 6, and that there's a lot of empty space in the shared economic pathways that has not been sampled with those like CMIP 6 scenarios, just because when you run a fully coupled Earth system models, that can be really like time consuming to finish those like a century runs. And so that you can see there's only 6 or 7, I believe there's less than 10 scenario has been sampled in this entire shared economic pathway, the scenario space, where what we are trying to do is to see if we can use the machine learning driven models to see how can we improve the efficiency of the Earth system model simulation, with the target trying to estimate or project the temperature, diurnal temperature range, precipitation, and the extreme precipitation. So what we found is that through an emulator, and it's not even those most complicated machine learning models, we tried random forest neural network and Gaussian process regression. So we both, with all those 3 baseline models, we are able to reproduce the spatial patterns as well as the accuracy of the Earth system model projections with much less computational cost on doing that. And with that, we produce a benchmark data sets. And with this 3 baseline model as a way to encourage the community trying to come up with a much more accurate way to do the Earth system model simulation through those machine learning methods that can really be part of the digital twin solution, trying to for the climate adaptation planning. With those, we can explore the much broad scenarios for the future climate scenarios. And with that, I'm happy to stop here and give us more time for discussion.
Thank you very much for your nice talk. In our panel discussion, we're gonna have 2 questions raised up by my side, and I'm gonna ask our panelists to give the opinion one by one, and then after that we also accept any questions, discussions from the audience. So the purpose of our panel discussion is pretty much trying to discuss about the current stage of how AI, machine learning, and the foundation models interact with the geoscience and the digital twin. There are a lot of, to be honest, anxiety in AI and machine learning researchers about because of the fast development of AI foundation models nowadays, and I think this also impact geoscience and digital twin domain. People may wonder, is there any opportunities and what is the current stage, right? So this is going to be pretty much the topic of our panel. So let me start to talk about the first question that I wanted our great panelists to give some opinion on that. The first question is, could you share the specific examples of how AI, machine learning, and foundation model techniques are currently being applied to support geosciences and digital twins related research? Who wanna start? How about Dr. Mai? Do you want to start?
Oh yeah, that's a very like general but very important questions. I can talk about it from like a more foundation model way, because I'm working on the related research for the past 2 years. So from my point of view, there are some very exciting advancements on developing foundation model for multiple or different geoscience tasks. One good example is Climate Act. So it's Earth System Science Foundation models developed by Microsoft and UCLA. So it's very good to discuss this after our another panelist. So they are working on the data set on tasks for the weather forecasting, short-term, long-term, mid-term, and long-term forecasting, but also focus on like downscaling and so on and so forth, but more focus on the large scale, like climate and weather dynamics. So this is one good example. Another example, I think maybe many of you already heard about that. It is like IBM and NASA collaborate and develop geospatial foundation model for based on multiple satellite applications, such as like land use tracking, natural disaster monitoring, and crop yield predictions, which I think this is very exciting, but they only pre-trained on like 1 year of Sentinel data. So basically, the foundation model is still multiple foundation model is like, although they are all for geoscience application, but they are focused on very different applications. Another exciting work is actually from our community, is Professor it's the work about autonomous GIS. So this is very exciting because they are using the idea for the auto GPT by using GPT-4 as autonomous LM agency, so that the user asks questions, so it can automatically divide the goal into several subtasks and say call ArcGIS toolbox or as geospatial function to analysis the data. So which I think is very innovative, and it's like a long-term goal for Esri or for QGIS, even for our oldest GIS software for the map. Another work is actually from a collaboration from Professor Injie and myself. So we are working on, say, using the foundation model such as ChatGPT and GPT-4 to do location description recognitions for disaster evacuation purpose. So when people, when the disaster comes, like a hurricane or with wildfires, where people will send tweets about their exact location address. So right now, there's a lack of very good techniques to automatically recognize the locations and geolocate them to the maps, because they are not very accurate, because different location description are very complex. For example, they can describe the intersection between two highways, or I'm in the front door of this building. So we, instead of just geolocate the whole highway or the whole buildings, we need to geolocate the very specific, because that's very important for disaster evacuation purpose. So we have using foundation model for that. So this is for, I think, very important applications I can think about.
Okay, thank you very much, Dr. Mai. Hi, Dr. Rao. Do you want to give some opinion about this question, this topic?
Sure. I think it's a very rapid development domain, and I think I put in the chat that NASA last month hosted a foundation model effort workshop on weather and climates, and their plan was, I believe, in the 6 months they're trying to complete their version of the foundation model in collaboration with Oak Ridge as well as with IBM teams on that effort. And so that there's a preprint in that on that website that you can find more details of a vision roadmap on that aspect of it. And another community machine on that is ML Commons. That ML Commons is really a community bringing those both industry as well as academic researchers in how developing those like leading practices and standards, where one of their group is a science working group right now, specifically looking at science foundation models. Because when we talk about foundation model, oftentimes the first thing people think about is the ChatGPT or those large language models. And now it has been expanded to the science domain. I think the challenge is that how do we deal with different types and different modality of the geospatial data in this case, where with language model that the data type is quite straightforward, where with the science, especially geoscience domain, that you have time series, you have imagery, you have LiDAR data points, and as well as in NOAA, there's also underwater acoustic passive acoustic data. So there are really vast variety of those data, and how when we're trying to do a foundation model in geoscience, dealing with those different type of data can be a specific challenge in that aspects. I believe at the climax that Dr. Mai mentioned that they have really specific way how they want to deal with different types of data in their foundation models, which is interesting to explore on that aspect of it.
Okay, thank you very much for your nice opinion on that. So my next question is kind of more outlook perspective of it. So in your perspective, what are the most promising opportunities in the intersection between AI, machine learning, and the geoscience and the digital twins? So can we just start from this time? Maybe start from Dr. Rao instead.
Oh, sure. So there are one thing I'm particularly excited about is that for knowledge discovery. So now I believe in a lot of groups are now looking at how can we accelerate scientific discovery with AI machine learning specifically, and not just trying to limiting to our current first principles of law. And then with NYU, there's a research group trying to use AI to discover more equations in the ocean systems, which is quite exciting that we are seeing a rapid development at this point. And I believe 3 or 4 weeks ago, NSF hosted AI workshop specifically looking at how AI can be used to accelerate the scientific discovery and engineering improvements. And that is really thinking about how it can address the gaps that the traditional technology cannot really address. So that is one aspect I'm particularly excited about. And the other part is to integrating those physical systems with the societal and economic systems, which with the AI and machine learning, that one example I showed is for the emulators, then now you can really easily integrate that into integrated assessment models, where you can explore much wider domain of the scenarios that with the traditional fully coupled Earth system model that can be quite challenging to do. So that the exploration of those, the possibility can be very promising.
Thank you. So Dr. Mai, do you want to give your take on this?
Can you hear me?
Yeah.
Yeah. So from my perspective, there are like several very interesting and exciting direction I want to explore. So first of all, we are thinking about more like spatial fairness and geographic generalizability. I think for now, most of the foundation model, all the AI models, when they applied on say geoscience tasks, they are actually like on say perform very differently on different area of the world. So, but as which is also called like a spatial replicability, according to Professor Michael Bouchard. So I think this is still a very challenging thing to tackle, especially in the foundation model kind of context. But it's also a general challenge for all the GeoAI research, especially for geoscience and digital twins. Another, I think, very interesting direction is how to handle heterogeneous geodata, for example, from different spatial and temporal resolution. So this is like the typically we want to take the different data from the different sources, and maybe they have different geographic coverage or different spatial resolution from different time. How do we use them jointly to perform some tasks? Yeah, these two directions.
Okay, thank you very much. So thank you. Okay, that was my echo there. Okay, sorry. I thought some people echo. So okay, let's welcome Dr. Yuan to give some question or opinion.
No, thank you for the opportunity to ask questions. And I actually have 2 or maybe 3 questions. It's more try to get a basic understanding of the presentation today. For example, we talk about digital twins, David, but what we say about twins is the identical copy of the physical things. And that's why it's so popular in manufacturers and in a lot of mechanical engineering. What do we mean by a identical copy of the Earth in the digital world? Can you give us some idea, how do we know we have achieved the digital twins of the Earth or digital twins of the world, and how similar, how identical it should be, and what will be the measure of degree of identical between the two? My second question is that what is the connection between foundation model and digital twin? And are they just 2 traits of different research directions with AI and machine learning in GI science? Or what would be the, are they mutually complementary to each other? And if so, how they complement each other? The third question is, my understanding of foundation models, they are transformers in some way, that they, based on what they have trained and the probability they learn from the data, and they can generate content. So it's also called generative models. But if we use it in geospatial, what kind of things we try to generate from the foundation model? And then how do we know the generative model or the result are even have any meanings geographically? And how can we use that? So I look forward to the responses and learn something from you all.
So if I can maybe take the first, and I may have to get somewhere by noon, but you asked very good questions, and I totally agree with you. I think the real goal of a digital twin, in my view, is focused on what you're trying to do at the end, and then walk back from that. And it may not be an exact copy. And the discussion you and I had about layers and objects, I think, is very apropos about, the PC pipeline locked us into layers. And I think digital twins are really going to want to know more about objects. And what is I don't think an exact copy is necessarily going to be true for every digital twin. But whatever level, there needs to be a level of abstraction, and that level of abstraction should bring a lot of value to the problem. And for example, if you maintain a very good digital twin for maps, and you're carrying around images all the time, that there's just too much data there, and you're just going to waste a lot of resources carrying around images. Once you get from a map or from an image to a vector, I think the vector is likely the intermediate storage, but that would be a 3D vector would be better than just a 2D vector, right? So I think the question should be informed by your what you're trying to achieve for your focused digital twin. And then as you walk back, you need to make decisions about what is the really value that your virtual model is, and what that's going to be. And in terms of foundational models, maybe those will be a digital twin. I think right now, from where we're approaching it from Oak Ridge, is those foundational models help us build digital threads to model whatever we're trying to model in the physical world through the virtual world. So right now, I'm not seeing them as a digital twin themselves, but as an enabler to get good models of whatever that intermediate stage is. So, and one last comment on the foundational models. We are spending a lot of time training tiny models and getting lots of trading data that's just taking forever on every little application that we need. If we had one foundational model that we just have to bend to the problem, we make that huge investment up front on the foundational model and then bend it as we go, that would be a lot better, because we have so many models at Oak Ridge that we've trained for so many different things. It's hard to keep up with, and we need lots of training data for every one of them.
Thank you very much for your nice answer. I also have some take about the second, third question, which was also very nice from Dr. Yuan. So my opinion is that I usually consider the potential of considering ChatGPT as being a digital twin for some specific person, if we can fine-tune everything of that person towards the ChatGPT, for example, right? So the ChatGPT can answer the question like me, right? So based on this kind of extrapolation, I thought if we can leverage the power of generation, like in the generative AI from the foundation models to help on some simulation tasks, in the digital twin, I think there could be some potential on kind of expanding this similar notion to that, and also let alone the historical application for AI technique to automate the collection, integration and processing of the data in digital twin. I think there are a lot of intersection and the potential between the AI foundation models and the digital twin. And of course, I'm looking forward to if there is any kind of opinion from the panelists and also audience towards Dr. Yuan's questions.
I do have a quick comment. I think there's also similarities between foundation model and digital twin, which, like David made a really good point. Like digital twin is really the use case or the task you're trying to address with that digital twin. And with the Destination Earth, they are piloting with different digital twin use cases, like the climate extreme weather, and then climate long-range climate resilience planning. And with the Climax, that Microsoft has been working on, for that foundation model, they also outlined downstream tasks that they want to address in that way. So in that sense, there are the similarities there that really focus on the downstream applications, downstream tasks between both digital twins and the foundation models. And I think going back to another comments, the similarity that I believe they all have is the requirement for the data, right? That the requirement for those high quality and then real-time ingest for those data can be really important for on both ends.
Okay, thank you.
I also have a short comments for the last question from Dr. Meiyuan. I think what she asked is a very important question, like why do we need to generate something? But from my point of view, the machine learning model can be generally classified into generative model and discriminative model. But I think even the model itself is a generative model. It's not only can be applied on like the generative tasks. For example, we can use the generative abilities to apply on more like deterministic tasks. For example, as what Dr. Ross said, we can use a Climate X foundation model from Microsoft to do some time series forecasting or the weather forecasting, which is more, from my point of view, is predicting the future. And also there are other tasks. For example, you can using prompts to ask ChatGPT a lot of geographic questions, say recognizing place names, forecasting about future for some time series about local places. And also you can give the GPT for vision maps and ask them to recognize some places from them. But although this is like a generated text, but they are also answer questions. So I think this is not only necessary to apply on like I just want to generate a new map or a new let's see remote sensing images, which I think is less useful for our domain. Yeah.
Thank you very much. Is there any more like opinions toward the question or any more questions? So I myself do have a kind of a question and curiosity because David has mentioned about the need to build some foundation models that can solve a wide range of tasks. But on the other hand, I heard from Dr. Mai about the current stage of the foundation models in GeoAI. So my sense is that the current stage is the task is still like a kind of more kind of specific, I would say. And so between this specific and generality, I just wonder how we can gauge the foundation model or how we can define the foundation model in Geo, how wide range the tasks we expect the foundation models for Geo to cover. I mean, this is my own curiosity. I just wonder if there is any opinion on that.
Maybe I can have a brief short answer. So you're right. I think many of the foundation model currently in like geospatial domain we have developed is focused on like very limited task set that can handle. So I think a more general goal or more ambitious goal is what OpenAI has proposed, like artificial general intelligence, where a lot of researchers doesn't agree with him. But foundation model, I think, is more like achievable concept, which say I only want to do a foundation model for this set of tasks. For example, segment anything. They only want to do segmentation-based task. But I think when we propose these foundation models, it actually aligned multiple tasks together, which can be considered as a building block to build a more like a more bigger or ambitious foundation model which can solve. I think this is like I like this kind of agile style, which can first solving a small set of tasks, but gradually increase your downstream task set.
Okay, so you consider this as a progressive process. Namely, maybe we start from like a bottom-up way, like currently we start from those smaller cases to make sure they work for specific cases, but gradually we found that they can share different knowledge across different tasks and finally build a model larger and larger, just like the trend in AI. We start from specific tasks and then kind of do collaborative learning more and more and then have a very large model. This is your opinion?
Yes. I think this is a long-term goal from my point of view.
Okay. Yeah, hey, thank you. So there are more question or opinion on this. I think this is a very good opportunity and see the community and we can discuss about the important questions like how to standardize like foundation models for Geo and for digital twin. So just wonder if there is any more kind of question or opinion. We are looking forward to that. Hi, Phil. You want to say something?
Yeah, I just want to say that this is a great panel and also keynote series. I learned a lot from this. I really want to say thank you to everyone. But maybe just a final question that from the AI machine learning perspective, obviously different aspects has been addressed today. For example, HPC, food supply chain, and from the organization perspective, how ESIP or NOAA is leveraging or what kind of obstacles you have to go through to leveraging it, and also how the latest foundational model could be used to automate a lot of process in earth science or geospatial domain. So what is the most challenging task that you think that the number one, just one thing that you think should be addressed in the near future about AI machine learning for geospatial sciences?
Thank you very much. I think these questions are very great and probably very suitable for our panel to answer. So yeah, Douglas.
The first challenge I believe is the data, and I think both the quality and access to those data can be quite challenging with the vast diversity as well as the volume of the data for the foundation models. And there are other aspects that I think right now a lot of people are talking about the ethics or responsibility of how we develop those AI technologies and the transparency of it. How can you explain those model output, especially when those outputs are being used to make those critical decisions like the emergency response or those critical decision-making process. And another, I think a lot of people are also started thinking about what's the energy consumption of those large models, and especially when you're doing the training and of those models, and how can we reduce the energy use, and then not necessarily the larger model is the better model oftentimes. So those are some challenge and some of the limitations I see there.
I just want to compliment what Dr. Rao said. I agree with this. Data set part is also a very important challenge. From my point of view, the most striking thing for me is what is a unique characteristic or challenges for geospatial tasks which require this geospatial foundation models. So which make it distinct from other, say, foundation models we have seen so far. Because when the foundation model comes, a lot of computer scientists will say, oh, I will develop this model. It is already suitable for maybe a lot of geospatial tasks. But from our point of view, what is some task or some challenges we cannot solve? One distinct one is it cannot handle the geospatial vector data. I do not see any foundation model which can handle that, but it's widely used in many of the GeoAI tasks. So either take as input or output. So we still think this is a very key challenges.
Okay. Thank you very much. Yeah, so I think there is no more kind of question, and we are also perfectly on time. So yeah, I just thank you again for attending this, and also I just want to give the time to Dr. Yang for if there is any kind of final kind of conclusion. Yeah, thank you.
Yeah, thank you, Dr. Zhao, for organizing and chairing this webinar. It's great. Really, AI machine learning for digital twins is the future for digital twins, and also for a lot of academic research that we have the opportunities over there. I really appreciate all the keynote speakers and panelists to share your insights. We will share the video and the slides. If you can't share, please send to us, and we will put on the website to benefit the broader community and share with through several channels. In the future, we will organize this on a monthly basis on different topics. So if you know an expert who's working on digital twins, and we should invite them, please let us know. And thank you, Dr. Zhao, Dr. Mai, Dr. Zhao, and Dr. Gao and Dr. Page. I know they have other commitment, but also thank you everyone for coming to this webinar. Bye.
Thank you.
Bye.